Welcome back to Comp 1405. In this chapter, we'll discuss recursion. Now, as the name implies, recursion is another way to bring repetition into our programs. At its simplest, recursion is just when a function calls itself, which causes that function to repeat. This is easier to demonstrate than explain, so let's start with a demo of a very simple recursive program. So in VS Code, we'll make a new file. We'll call this recursion.py. And I'm going to define a very simple recursive function. We'll call this loop. And all this will do is print the word loop and then call itself. But what happens when a function calls itself? Well, once we call our function, we jump to the top of that function, we print out the word loop, and then we call that function again.
Which means jump to the top of that function, print the word loop, and then call that function again.
Which means jump to the top of that function, print the word loop, and call that function again. Which means jump to the top of that function, print the word loop, and call that function again. Which means jump to the top of that function, print the word loop, and call that function again.
And this is how recursion causes repetition. Note that we haven't told this program to stop at any point, so in effect what we've written here is an infinite loop. So let's save and run our code. We'll say Python recursion.py, and it prints out the word loop a whole bunch, and then it crashes. We get what's called a recursion error. The description reads, maximum recursion depth exceeded while calling Python object. Looking through our stack trace, we can see the code crashed when we called the print function on line 2 in our loop function, which was called from line 3 in our loop function, which was called from line 3 in our loop function, which was called from line 3 in our loop function. And notice this repeated about 1,000 times before it was called from line 5 in the main module. So that's the starting call. So as we can see, this code repeated a whole bunch, but then it eventually crashes with maximum depth exceeded. So it's not infinite after all. To see what's happening here a bit better, let's modify our code to count how many times this function calls itself. So we'll say loop, and pass in a value I, which when we start it will be the value 0. But then when we call our function again, we'll pass in I plus 1. So the first time it'll be 0, then 1, then 2, then 3. And instead of just printing the word loop, let's just print the value of I. Save and run our code again. So now it printed out a whole bunch of numbers from 0 all the way up to 996, and we got the same error, maximum recursion depth exceeded. So the same thing happens, but this time we see it counts to almost exactly 1,000. This limit is imposed by Python itself on the size of our call stack. You might recall the call stack from chapter, I believe it was 5, when we first talked about functions. So every time a function call is made, we have to reserve space in memory on the call stack or the program stack for that specific instance of the function call. So if Python had let this infinite loop run forever, it would eventually fill up all of our memory and our computer would become unstable. So instead, Python says the call stack can't ever be greater than 1,000 frames deep. You might note this is not a problem with a standard infinite while loop. That can run forever without adding anything extra to the stack. If we want our recursive loop to stop, we can add a condition into our function. So I can say, for example, with this variable I, if I is greater than some value like 100, then we can return. Return means leave the function, and if we hit that before we call the function again, then we won't call the function again, and that'll stop this loop. We can also, instead of saying a hard-coded 100, we can make this some parameter. So I could say pass in some value n, and when we start the loop, we'll give it some stopping condition of 100 steps. Notice when we call the function again, we will want to also pass that variable through. Save and run this code. And now we can see it runs for about 100 iterations and then stops. So recursion is a new approach to repetition using functions, but it requires a slightly new way of thinking. So before we get to solving problems with recursion, let's start by learning to think recursively. The general idea behind recursive thinking can be summed up in two parts. Part 1 is, if I can solve the problem easily, then I'll just do so. If it's easy enough to be solved in a single step or even less than that, then great, the problem's already done. And otherwise, if I can't solve it right away, then I'll solve one step of that problem and start the process over with the remaining smaller problem. As a demonstrative example of this, imagine you were standing in some very long line and you couldn't see the front of it, and you wanted to know, what spot in line am I standing at? Now if we wanted to solve this problem iteratively, that is to say with a loop, we would get out of the line and count each person as we walk towards the front of the line. Once we get to the front of the line, we've counted each person, we know exactly which spot we were in. Now we've lost our spot in line, but that's not really relevant in this example. If we wanted to solve this recursively, we could do this without leaving our spot in line, we could just ask the person in front of us what spot they're in. And if they tell us what spot they're in, we can just add 1 to that. If I know you're at spot 100, then I know I'm at spot 101. However, in order for them to get their answer, since they don't know what spot they're at, they'll have to ask the person in front of them, who will have to ask the person in front of them, who will have to ask the person in front of them. Eventually, this question will propagate to the front of the line. Now, the person at the front of the line knows they're at the front of the line because there's no one standing in front of them. So, without even thinking, they can turn to the person who's second in line and answer, I'm obviously first in line. So the person behind them knows that they're first plus 1, which makes them second in line. And the person behind them then knows they're third in line. And then the person behind them knows they're fourth in line. Eventually, this answer will propagate back towards us. The person in front of us will say, I'm at position X, and we'll then know we're at position X plus 1. So if they say I'm at position 100, we'll know we're at position 101. So again, to think recursively, we're going to solve one small step and then start over with this smaller problem. So in its simplest form, recursion is just when a function calls itself. But in order for this to be an effective problem-solving technique, a recursive function needs to have 3 key features. These parts are known as the base case, the recursive case, and the step. So the base case is what solves the problem when it's trivially sized. So the base case tells us when to stop repeating. The recursive case, this is where the function calls itself. This is what causes the repetition in our recursive program. And the step is something that makes progress towards that base case. So something in the recursive case must shrink the problem so that eventually we will get to that base case and our program will stop. Otherwise, well, as we've seen, we'll run into this infinite recursion right up until our call stack fills up and we'll get what's known as a stack overflow, or in Python, just a recursion error. So the basic structure of an effective recursive function can be seen in this flowchart. So we have some function called f. The first thing it does is asks, am I at the base case? If so, then we're done. That's the end of it. We can solve the problem trivially. If we're not at the base case, then we take the false branch, we take some step towards that base case, and we call our function again. Now, when we call that function again, it creates a second instance of this function. So it's like we have another copy of this flowchart. So it jumps to the top of that function, and we walk through our code again. We ask, are we at the base case? Let's say we're not, so we'll take a step towards that base case, and we'll call f again. Now we'll walk through the code. For the sake of argument and for the sake of space on this slide, we'll say now we are at the base case. So we take the true branch and it says return. Notice that doesn't mean exit all of our process. That means just exit this current instance of the function. So when we return back to where the function was called. Now if there happens to be more processing in here, we'll do those steps. This is again just the basic structure. But if this function is now done, it will return as well. And we're back in the original calling function. That will eventually return as well, and our whole process will be done. To see recursion in practice, let's do another simple demo function. So this one, we'll call it def write stars. And the challenge here will be, given some value n, we're going to print that many stars or asterisks on the screen. So prints n asterisks stars on the screen. Now this problem is quite straightforward. In fact, we could solve it iteratively in pretty much a single line. So I'll just demonstrate that with code here. I'll say iteratively for I in range n, print, and then we'll just print out an asterisk. So if I call write stars with, let's say 10, save and run our code, Python recursion.py, and we get 10 asterisks printed to the screen. So it's pretty easy with a loop, but let's see if we can't now solve this using recursion. So to solve this with recursion, we need 3 main parts. We need a base case, a recursive case, and a step, something in that recursive case that moves us towards the base case. So it's usually a good idea to start by thinking through what would your base case be. So the base case, and it's called a case because it depends on what your inputs are usually. Certain states of your input will result in this base case. And whether that's input from the calling program or input from the recursive repetition, either way, because this function is going to be called by both, the function needs to eventually reach a point where it can solve the problem trivially. So what is a trivial version of the write stars function? So if I asked you to write n stars to the screen, what's a value for n that you could do that without actually having to do any work? Hopefully you've realized if the value of n is 0, if n is equal to 0, then we're already done. We don't have to print anything. So we call this the base case. We'll call this recursively. We're going to solve this, and there's our base case. So in the base case, we want to stop repeating. So we'll just say return. It's the end of our repetition. Now if we're not in the base case, so we can say else, which means we're in the recursive case. In the recursive case, though, we need to take a step towards our solution. So what's one step of printing n stars? In that case, that'd be printing 1 star. So I'll just say print and then a star. And if we want just to make these all on one line, so our output's a bit more condensed, we'll say end equals, and we'll get rid of the new line at the end of our print statement. So print 1 star without /n. And then what's left to do? We've printed 1 star. The user asked us to print n stars. So we still have n minus 1 stars to print. So we'll call our function write stars with an argument that's slightly smaller, 1 step smaller. So we could say this is the step, and this is the actual recursion. So let's save this and run our code, see if it works. So save Python recursion, and looks to be about 10, but let's try it with a different number that's easier to count. And that's 5 stars. So this example isn't much different than the loop function we already created. We're just printing values and shrinking the size of our loop each time. In this case, we're counting down from n instead of up to n, but it's the same idea. So this is an example of a recursive program that solves some problem. In this case, the problem of printing n stars to the screen. And importantly, we have 3 key parts. We have our base case, which says for some trivial value of our inputs, we're done working. We can solve this problem without doing any work. We have our recursive case, which calls our function. And then we have a step, which does 1 step of the problem and ensures that when we call that function in the recursive case, we're calling it on a smaller version of the problem, so that we're eventually going to reach that base case. Note that if I don't include this -1, the part that shrinks our problem towards our base case, then our loop has no reason to stop running, and so it's going to keep executing until Python stops it, when we reach the maximum recursion depth. Okay, so let's put that back in there so that that doesn't break our code. And let's move on to another example. This one from our slides. This one says, create a recursive function called fac of n that calculates n exclamation point, which means n factorial. It's the multiplication of all the numbers underneath n. So if we have 5 factorial, that's 5 times 4 times 3 times 2 times 1. If we have n factorial, that's n times n minus 1 times n minus 2 times n minus 3 times 3 times 2 times 1. So let's make space for another function here. And we said this one's called fac of n. This will compute n factorial, which is defined as n times n minus 1 times n minus 2, all the way down 3 times 2 times 1. With a loop, we could solve this pretty straightforward, but we're going to do this with recursion. So let's look at a recursive definition. So think, what's a value for n where I could compute the factorial of that value without doing any work? That is to say, what's the base case for this recursion? Since we have this iterative definition, we can see the end of that list of values is the smallest value 1. So that's a hint that that's going to be the last value in our recursion as well. And in fact, if we think what's the value of 1 factorial, well, that equals 1. So that's pretty easy. And now can we come up with a recursive definition that will eventually get us down to that 1 factorial? Well, we can say n factorial equals and then think, what's a single step of that process? Since we're calculating the product of a long sequence of values, then a single step would just be a single multiplication. So we can say n factorial equals n times the rest of that problem, so n minus 1 factorial. Where this exclamation point represents a call to the function to compute n minus 1 factorial by saying n minus 1 factorial is n minus 1 times n minus 2 factorial. Now with this recursive definition in place, our code should be pretty straightforward. So we need a base case, which is if our input, n, is equal to the value 1. You should note that this time our function needs to compute and return a result, so it's a little bit more complicated than what we've seen, but it's still pretty straightforward. If n equals 1, then we're going to return 1. So 1 factorial has a value 1. Then we have a recursive case, which is to say else, which we don't technically need the else because our base case returns. So if this condition were true, we're not going to reach the recursive case. But if it were false, then we'll hit this recursive case, at which point we'll say return, and then this information here. So we have some value n, and we need to compute the n minus 1 factorial. So we'll say n times the fac of n minus 1, where that's our function for computing factorials. So notice we have a base case where we're stopping our repetition, we have a recursive case where we're repeating, and we have something in that recursive case that makes our problem smaller so it will eventually reach the base case. So I can say the factorial of 5 and call Python on recursion.py. That didn't do anything because I forgot to print the output, as is tradition, so I will print the factorial of 5, and we can see it's 120. So 5 times 4, which is 20, times 3, which is 60, times 2, which is 120, times 1, which is still 120.